Okay, good morning grade 11s. This is the second video in the Euclidean geometry series. We're going to go on to Theorem 2, but it's very similar to Theorem 1. It's kind of play off on Theorem 1. So basically what they are saying is the perpendicular bisector of a chord passes through the center of a circle. So in other words, if it's bisecting, so these two lines are equal and it's perpendicular. So that piece of information it's perpendicular and it bisects. They're saying that it then this line has to run through the center of the circle. Okay, they don't tell you what the center of the circle is. All they're saying is if it's a chord, it bisects the chord and it's perpendicular to the chord, it must run through the center of the circle. Okay, so I wrote here it's the same kind of proof as Theorem 1 because they also use congruency to prove this, just slightly different information. Okay, so what you're going to do is you're going to draw a random point on this line, and you can call it whatever. I've just called it R here, and you're going to connect RB and you connect RA. So that is what you construct, okay? Like I wrote here, construct RA and RB. Okay, now what we're going to do is we're going to look at these two triangles and you're going to use congruency. So in these two triangles, we agree that angle D1 is equal to angle, okay, they call it D3 here, but anyways, these two D angles, D1 and D2, they are equal because they are perpendicular. So they are both 90 degrees. So you can say D1 equals D2, which is 90 degrees because CD is perpendicular to AB. So that was quite straightforward. Then we say AD, this line, is equal to DB. That was just given to us. They told us that those two lines were equal. They said it bisects that line. So that's fine. And then you know that RD is common. You can see it lies between those two triangles. So that is common. So if you look at it, you've given an angle and you've given two sides. So when you say they are congruent, you're going to use SAS for side, angle, side. Okay, if you were tempted to do what you did in Theorem 1, where you say RB and RA are equal because they are radii, is that correct? Can you say that? Is R the center of the circle? Do you know if that's a radius? You don't. So you cannot say RA and RB are equal because they're radii, because we drew R in. We don't even know what the center is. We're trying to prove that this line runs through the center. So you cannot assume that that's the center. Okay, so what we've used is what they've given us. AD and AB, that's equal. We've used that RD is common, this middle line is common, and we've used that those two angles are equal. So this is SAS, side, angle, side. Okay, so because the triangles are congruent, they're identical triangles, this line, RA, must be equal to RB. Okay, so now all you can say after that is this proves that any point on CT is equidistant from A and B. So any point that we put here will be equidistant from A and B. The center of the circle is also equidistant from A and B. So CT must pass through the center. Okay, so that you'll just write afterwards. Remember, equidistant means it's the same distance. So RB is the same distance from RA. So if the center of the circle will also be the same distance, therefore it must run through the center. Okay, so I'm not going to, like I say, I went through this quickly because it's very similar to Theorem 1. But just run through it. You're using congruency again, but just make sure this time you use SAS because you don't have the hypotenuse because they're not radii. It's not, you don't know if that's the center of the circle. Okay. All right. Theorem 3. This one is slightly different. I'm going to use some colors because all of these cases are slightly different, but they follow the same idea. Okay, so with this theorem, what they want to prove is that the angle at the center of the circle is double the size of the angle at the circumference. Now what I mean by that is if you look here at angle O, that's this one over here, they are saying that angle is double the size of that angle. Okay, and then in diagram 2 it's the same idea. This angle, even though it's reflex, is double the size of this angle. You can see that's a reflex angle, so it's larger than 180, but it will be double the angle of P. Okay, and then the same thing over here. Even though this one looks very strange, it's still so if you look from A and B, that subtends the angle towards the center. Then the same little 2 points subtends it to the circumference. So this angle O, they're saying, will be double the angle of P. So you'll notice it always gets subtended from the same 2 points. So here it was subtended from AB to the center. Then from AB again, it's subtended to the circumference. Here's AB, it's subtended to the center, and then again to circumference. AB to the center, AB to the circumference. Okay, so it's always from the exact same 2 points. It gets subtended to the 1 point, and then subtended to the other point. And basically, if that is true, if they come from the same point, they are saying that angle O will be double the size of angle P. Okay, so we're going to run through this proof, and then I'm going to do an example with it. But for this to work, I'm going to highlight the triangles that we're going to work in. So what you're going to do is you're going to construct PQ. So you're going to draw this dotted line in. You see PQ there. You're basically dividing up the triangles. In diagram 2, again, you'll construct PQ. And for this one, again, PQ. So PQ runs through O. So here's P runs through O, and then Q will be your other end. P runs through O. P runs through O. Okay, so now let's look at our 3 different cases. What I'm going to do is highlight the triangles so you can see them. So that's the first triangle. Okay, let's do this one as well. There's one triangle. Okay, and then let's do this one. So it's PAO. PAO. I want them to be the same. Okay, now let's do a different color for the other triangle. So POB. POB. Here's another. POB. And here, POB is this little one this way. Okay, you're gonna see why I highlighted it. It's just gonna make our lives a bit easier. All right. So we're going to get started. Now, for these two, they have the exact same proof all the way. And for this one, the end of the proof differs ever so slightly. Okay, so both of them, all 3 of them will start the same way. So I'm just going to write here. So I'll write the first bit of proof and then I'll change as we go. But as we're starting off, do you agree with me that if you look at this pink triangle, so look at only the pink, PAO. Angle O1, that little one over there, is an external angle. Remember when let me just show you here to remind you. If you have a triangle that looks like that, this angle will be equal, so let's call that X, let's call that Y and Z. Angle X will be equal to Y plus Z. That's just exterior angles of a triangle. It's a theorem. You know this. So X is equal to Y plus Z. So the exterior angle is equal to the 2 interior opposite added together. So not the one that's next to it. That's something else. So it's just those 2. All right. So if you look at PAO, that triangle, angle O1. Okay, so just by the way, remember to start off by saying required to prove that. Okay. All right, but anyways, angle O1 will be equal to angle P1 plus angle A. Okay, and by the same token, angle O2, so if you look at the orange triangle, angle O2 is equal to P2 plus angle B, because this is exterior angles of a triangle. Okay, both of those are triangles, and that exterior angle will be equal to the sum of the 2 interior opposite. And if you look at the other 2 diagrams, you'll see it works out nicely as well. Here's your pink triangle. So O1, that angle over there, must be equal to P1 plus A. There's the two interior opposite. And O2 must be P2 plus B. Okay, then if you look at this diagram, you'll see it's exactly the same. Here's your pink triangle over here. So angle O1 is the same as P1 there plus A. And then if you look at your orange one, this whole angle O2 will be equal to P2 plus B. Okay, so we've established for all three of those diagrams, they're exactly the same. Okay, then our next step. Remember I told you always look out for radar, because radar means, you know, it's from the center of the circle to the circumference, the length will be the same all the way around. So if you look at this line here, OP, then you look at OB, and then you look at OA. They are all radar, so they must all be equal. Look at the second diagram, OP, OA, and OB. Same in the third one, OB, OP, and OA are all radar, so we can say that they are equal. OP, OA, and OB are radar. Okay, so they are all definitely equal. So if you think about it, now that you know, look at these, let's just look at the first diagram. These two triangles, we know that this length equals that length. What kind of triangle does that make that triangle? It makes it an isosceles because the two sides are equal. And what do you know about the base angles of an isosceles triangle? They are equal. So we know that angle P1 is equal to angle A. And then in the orange triangle, so the same must be, because this is radar. OB equals OP. So this is also an isosceles triangle. So angle P2 is equal to angle B, right? And it's the same in these triangles. Look, here's your two equal sides. So this P1 must equal A. And then you look into the orange triangle. Here's your two radar. So P2 must equal B. Same thing in your last triangle. Here's your two sides, your two radar. So P1 equals A. And then in the orange triangle, OB equals POP. So P2 must equal B. Okay, so we've established in all three of those circles and with all the triangles, we can say that the angle P1 is equal to angle A. And angle P2 is equal to B. Now you can say base angles of an isosceles triangle or angles opposite equal sides. Let's just do angles equals opposite side. Angles opposite equal sides, just because it's more commonly used. Okay, so now we've established that these two angles are equal to each other. All right. But now let's go back to the first point that we made. Angle O1 is equal to P1 plus A. But now we've established that P1 and A are also equal to each other. So O1 should actually be the same as P1 plus P1. Do you understand what I'm saying? And angle O2 is the same as P2 plus P2 because P2 and B are exactly the same thing. They're equal to each other. So therefore, you can say angle O1 is equal to 2P1 because P1 and A are the same and O1 are the same as adding those two together. And O2 is equal to 2P2. Okay, you don't have to write any reason because you've just proved that in the previous things. Okay, so therefore, now remember the whole goal of this was to prove that angle O, okay, is twice the size of angle P, correct? So, okay, so this is where diagram 1 and 2 differ a little bit, okay? So for this angle O, O1 plus O2 makes up the full angle O, correct? So I'm just going to say in diagram 1 and 2, Okay, so let's just do it in a different color. In diagram 1 and 2, angle O, right, is equal to angle O1 plus angle O2. But now we've established that O1 is 2P1. So it's the same as 2P1 plus, and O2 is the same as 2P2. Okay? Which could then be factorized. Do you guys see there's a common factor of 2? So this is equal to 2 times P1 plus P2. Okay, do you see that we have proved what we need to prove? Because you've now got it that O1 plus O2 is equal to 2 times P1 plus P2. And you were looking for that. You wanted to prove that angle AOB is twice the size of APB. So now you could say, therefore, angle AOB is equal to 2APB. So we have proved what we need to prove. By the way, just a reminder, you always start with RTP, what you need to prove, and then you end off with that to show that you have proved it. Okay, now remember I said that works for diagram 1 and 2, but you couldn't have said O1 plus O2 because this diagram you're only looking for O2. This angle is O2. I mean, it's O2 minus O1. It's not the whole thing. Okay, so now we're going to say in diagram 3, so we can just do the last one. In diagram 3, you just want this little piece, this angle here. The whole thing is O2 and that piece is O1. So to get that piece alone, I'm going to say O2 minus O1. Okay, and we've established that O2 is 2P1. So it's 2P1 minus 2P2. And again, if we factorize, it's 2 times P1 minus P2. And if you look over here, sorry, actually, I think I meant it the other way around. Let me just fix it. Well, I'll just scratch it out. So it's 2P2 minus 2P1. P2 minus P1. Okay, so if you look here, the whole thing is P2 minus P1 gives you that little section over there. The same thing as over here, it was the whole of O was O2, but if you minus the 1, you just get that little piece over there. So it's 2P2 minus 2P1. Okay, and then if you factorize it, you can take out the 2 again, and then you'll see that this is double. Okay, so again, I can write, therefore, AOB is equal to 2 APB, and that is proven. So just make sure when you're using this one for diagram 1 and 2, just remember that you'll add them, and for diagram 3 you must subtract because it's a little bit different, and you'll notice that when you look over there. Okay, all right, now let's do 2 examples, and then I will give you a different video for theorem 4. Okay, so just as a reminder, I drew these 3 circles for you. So what they're saying in this theorem is that this angle here, if that is, or if this angle is x, this one will be 2x because it's double the size. Same with this one here. If this is x, this will be 2x. And even with diagram 3, even though it looks a little bit different, same thing. The angle is subtended to the center, so that would be 2x, whereas the one at the circumference would be x. So this one would be half the size of that one. Okay, so look at diagram 1. They've told us that this angle is 150 degrees. Okay, now we need to go and find x, w, and v. Now I don't want you to get confused and think that this 150 relates to the v. Okay, look at this diagram over here. If I drew my angle from, let's say this is A and B. If I drew from A and B to the center, and then I draw again from here to the circumference, do you notice that this angle and this angle goes together? But if it's a reflex angle, if it goes this way, okay, then it's this angle that goes with that angle. Okay, so just make sure you pair them up properly. So clearly this V, okay, it matches with the x. Those two are drawn together. This reflex angle W is what goes with the 150. So just make sure you pair them up together properly. Okay, so remember we've now established that the center one is double the size of the circumference. So we're going to say W is equal to 2 times 150. And I didn't even give you the reason. So let me just write it down so you can add it into your theorem. Whenever you use this, your reason is going to be angle at center is equal to 2 angle at circumference. Okay, so over here, the fact that, so now we've written it's 2 times 150, you must say angle at center is 2 angle at circumference. Okay, so W is equal to 300. As you go, fill things in because it will help you. So this W is 300. Okay, now how would you propose we get V? If this is a full revolution, we know a full revolution is 360 degrees, so that's easy. V would just be 360 minus 300. You can just write revolution equals 360 in your bracket. So V is just equal to 60 degrees, so we know that's 60. Okay, now again, you've got this angle at center, angle at circumference situation. So this is 2 times this angle. Okay, so that 60 is double the size of x. So x would have to be 60 divided by 2. Reason being angle at center equals 2 angle at circumference. Alright, so x is equal to 30. Okay, I hope that makes sense. So now you've gotten all of those angles. Like I say, please remember to pair them up correctly. It's like the opposite one goes with the one at the circumference. Number 2, example number 2. This is more like diagram 3. So just make sure when you match them up, you match them up properly. So they've told us, I know you can't see this properly, this is 80. Maybe you can't read it from there, but this is 80, this is Y, and this is Z. Okay, so they want Z over here. Now, actually I feel like there should have been more that they asked for. I just make double sure. I don't have any examples. I'm not sure where I got this example from. Okay, well, anyways, I thought there would be an X that they would ask for, but they've only asked for Y and Z. Okay, so the first thing that I want you to notice is that there are parallel lines here. So with parallel lines, what shape does this make? This is your alternate segment. So you know that Y and Z are equal to each other. And the same the other way around. So if I draw my Z this way, we know that this 80 is the same as this angle P. So let's go and fill in angle P, because that we know. So angle P is equal to 80, reason being alternate segment. And just remember that you should always fill in your parallel line. So you can say AO is parallel to BP. Okay, so now that you know this is 80, now you can use your theorem. Remember, this looks very much like this. So the angle subtends from AB to P, which is 80, and the angle subtends from AB to O. So this angle Y should be twice the size of angle P. So we're going to say Y equals 2 times 80. Reason being, angle at center equals 2 angle at circumference. Alright, so Y is then equal to 160. So we know this is 160. Okay, now I already helped us a little bit by drawing that first Z. we know that y and z are equal to each other because of alternate segments. So then you can say, therefore, z is also equal to 160 because alternate segment, and then make sure again you put in your parallel lines. Alright, okay, I hope that makes sense. I'll find you an exercise that you can do with this theorem.